Assalamu alaikum everyone. I'm Dr. Ahmed AlEroud. I'm working as an assistant professor at Yarmouk University in Jordan. So the title of my presentation is Anonymization of Network Traces using Noise Addition Techniques. So I will talk about data sharing and traffic anonymization. I will talk about the challenges of anonymizing network data, the objectives, the sensitive network attributes, existing anonymization techniques, experiments and evaluations, and then I'll go over conclusions and future work. So there are many benefits for sharing network data, for collaborative intrusion detection, and advancements of network research. However, nobody wants to share their data due to many reasons, including sensitive information and some privacy concerns. What is the solution? So the solution is to do anonymization or encryption of network traffic. However, we want to do that anonymization in a way that keeps the data still useful for researchers and at the same time private enough for people who want to publish their data. So is it possible to create a technique that can still be used for threat intelligence or threat analytics while at the same time has a minimal privacy violation? So first we need to know what are the sensitive network data that we need to protect, and to what extent these encryption techniques can be still used to predict cyber attacks. There are many sensitive network attributes, including IP address, MAC address, timestamp, port number, and counter information. Some existing encryption techniques for network traffic includes black marking, truncation, permutation, and other prefix preserving permutation. However, none of these techniques preserve the quality of the data, meaning that they just destroyed the data. Encryption or anonymization techniques that keeps the research value of the network data and at the same time is private enough. On the second hand, we want to make sure that this encryption technique is immune to traffic patterns in the collected data. We still need to make sure that these injected patterns cannot be recovered by using non-text attack. So we propose a novel methodology that actually rely on a machine learning techniques called differential privacy, which can be used to avoid data injection attacks and at the same time preserve the quality of the data, the collected data. So this is a description of my methodology. I'm not going to go into the technical details of this methodology. As I said, differential privacy is actually a new technique to preserve the quality of the data. And at the same time, we could publish this data and use it for analytics. This slide summarizes what we mean by differential privacy. I can share or publish network data by adding something called Laplace noise on the original data and then publish that data for researchers. So we, in this case, we preserve the privacy of data and at the same time it can be still used for threat intelligence and cyber attack analytics. By adding this noise to the data, there is a mathematical guarantee that, even if the attacker injects some patterns in the data, he will not be able to specify the individual records. Given the original data, if I add a new packet count to this data or a new record, the attacker cannot reveal the added value. Which is the major objective of differential privacy. Here's a summarization of our algorithm. We cluster the data into different groups and after that we add the Laplace noise to each group to make sure that the collected traffic is private enough. There is another algorithm, it's called condensation. It works on a similar manner to differential privacy. However, the type of noise added here is done in a different way. Taking the original IP address, we did permutation and then clustering on the first few digits of each IP address, and then we take the average of the values in each clusters. This is called condensation and or microaggregation. So as far as we increase the value of the cluster or the number of records in each cluster, we achieve more privacy and less with risk counters. Experimentally, we did our experiments on the predict datasets. As everybody know, that it's really hard to get labeled intrusion detection datasets. And we did an experiment on the University of Twente datasets. This is a public network dataset. This slides show that when we use differential privacy, we still can achieve high intrusion detection rates, meaning attack prediction, while at the same time I can share my data with researchers so that they can use it for threats analytics. Privacy results, we measured the privacy of the resulting data by comparing it to the original data using a conditional privacy measure. Our method, which is a differential privacy, achieves higher privacy than other existing techniques. On dataset 2, we did the same experiments, classification and intrusion detection. We get the same consistent results. Differential privacy has good results. This is another experiment on the privacies. It shows that if differential privacy is good enough to achieve privacy and at the same time get high accuracy when we do intrusion detection. Finally, we tested our method against injection attacks. If somebody injects some traffic patterns and want to know what is the encryption algorithm or anonymization algorithm we used, we injected 5 patterns, 130 records, and then we tried to recover these methods using different anonymization techniques. We applied 5 different anonymization techniques, including differential privacy. This slide shows how can we successfully recover the injected patterns using the traditional anonymization techniques, while this is a failed attempt to recover the injected pattern when we use differential privacy. Finally, this slide shows the experimental results, the recovery rate of the injected patterns. All methods, we can still recover the injected patterns, except for our methods, we were unable to recover any injected patterns, meaning that differential privacy can achieve the good amount of privacy and at the same time preserve the quality of the data. So our method is robust against injection attacks. It has a stronger privacy guarantee. It has achieved better privacy than existing techniques. We'll try to system. We'll try to apply these methods in a big data setting, and finally we will try to use additional domains with cybersecurity to apply our methods on. Thank you very much.
We have 15 seconds for a question. You don't have to run, it's fine. Any questions? All right, thank you, Ahmed.
Thank you
very much.